We talked earlier about constant volume calorimetry, where we were using that bomb calorimeter, which is, fancy piece of equipment. Now we're going to talk about constant pressure calorimetry, and we can do this in something as simple as two nested styrofoam cups. Here they're showing a cork lid. When we do this in lab, we've got cardboard lids, right? So the nested styrofoam cups are for insulation because we don't want significant heat loss to outside of the calorimeter. We'd like to keep it to the water inside. This is open to the atmosphere, so it's going to be at constant pressure. So Q for the solution, we can calculate from the mass of the solution, the specific heat capacity, and the change in temperature. So that's why the thermometer's in here, so we can measure the change in temperature. Any heat that the solution gets has to have come from the reaction. Any heat that it loses must go to the reaction. So Q for the reaction is the same number as Q for the solution. The sign is opposite. Q for the reaction equals Q at constant pressure, which is delta H for the reaction, the enthalpy of reaction. As we learned, delta H is generally expressed as joules or kilojoules per mole, based on how many moles are in the chemical equation. And so we get that number, and then we're going to divide by the moles that reacted. So here is an example. The addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to this reaction. When 50 milliliters of 0.1 molar silver nitrate is combined with 50 milliliters of 0.1 molar hydrochloric acid, in a coffee cup calorimeter, the temperature changes from 23.40 degrees Celsius to 24.21 degrees Celsius. Calculate delta H for the reaction as written. Use 1 gram per milliliter as the density of the solution and a specific heat capacity of 4.18 joules per gram degree Celsius as the specific heat capacity. That's a lot of words, right? So we read all the words. Now we're going to go back and highlight. I guess I should include that. Highlight these numbers. We've got a couple temperatures here. We've got a density, specific heat capacity. Those are things we're given, and we want to calculate delta H. So that's not what I meant to do. So what we want to end up with then is the heat of reaction over here. So this kind of looks like a stoichiometry problem because we have a volume and a concentration and a volume and a concentration, and we've got a chemical reaction occurring. And it could end up being, you could have a stoichiometry problem with a limiting reactant issue here, but that's too much. If we look at this, the same volume of the same concentration, they're both 50 milliliters, both 0.1 molar, so that's equal numbers of moles, right? And in the balanced chemical equation, it's 1 mole of this to 1 mole of that. So this is set up so it just all reacts and there's nothing left over. So we don't have to calculate a limiting reactant. We don't need to calculate an amount of product. We just want to calculate the amount of heat that was gained or lost by this reaction. So we know that Q for the reaction is equal to negative Q for the solution. So we need to find Q for the solution, and that is going to be the mass of the solution times the specific heat capacity of the solution times the change in temperature for the solution. So we've got some temperatures here. We've got 23.40 degrees Celsius and 24.21 degrees Celsius. So it went from 23 to 24, so that's our initial and final. And so then delta T will be the final minus the initial, 24.21 minus 23.40, 0.810 degrees Celsius. So that's delta T for the solution. And we're given the specific heat capacity, it's right there. So the other thing we need is the mass of the solution. Well, they didn't tell us what the mass was, but they gave us information about the volume. If I mix 50 milliliters of this and 50 milliliters of that, what's the volume of the solution? 50 plus 50 is 100, right? Just going to kind of scribble that out down here. So 50 milliliters plus 50 milliliters gives me a volume of 100 milliliters. I want the mass. They told me what density to use. I've got volume and I want to calculate the mass. So I'm going to multiply by grams and divide by milliliters. And then I see that the density is 1.00, and that's where the gram is, and so we end up with 100 grams is the mass. So I have all three of these quantities. So Q solution then is equal to the mass, 100.0 grams, and the specific heat capacity, 4.18 joules per gram degrees Celsius, and the temperature change, 0.81 degrees Celsius. The units are going to cancel out, and I'm going to end up with 100 times 4.18 times 0.81 equals 338.58 joules. And I'm keeping track of my significant figures. The temperature here only has 2. So that's Q for the solution. Q for the solution, well, let's do it this way. Q for the reaction, right, is negative Q for the solution. So that's going to be negative 338.58 joules. That's the heat for this specific volume and concentration. But we want to know how many joules per 1 mole of silver nitrate. So I need to take this amount of joules and divide by the moles of silver nitrate. Can I find the moles of silver nitrate? Yeah, I've got 50 milliliters and 0.1 molar. Right, so 50 milliliters, let's do it this way, 50.0 times 10 to the minus 3 liters times 0.100 moles per liter. So I'm going to divide by the moles, 0.005. .00 moles. So negative 338 divided by 0.005 is going to give me negative 67716 joules per mole with 2 seconds. This is a big number, 67,000. So normally we would convert that to kilojoules. So here we're going to have joules on the bottom, kilojoules on the top. 1 kilojoule is 10 to the third. And so we're going to get minus 67.716 kilojoules per mole, which is negative 68 kilojoules per mole. Any questions? Can I explain why it's negative? Yes, I believe I can. So we can observe the temperature of the solution. The reaction is happening in the solution, but the solution is mostly water. The solution is not actually the reaction. So we see that the solution heated up, right? It got warmer. Where did that energy come from? It came from the reaction. So the reaction lost energy and the solution gained it. So that's the kind of thinking about it way. Just looking at the math, we know that Q reaction is equal to negative Q solution. They have to be opposite in sign. It's the same number, but one's negative, one's positive. So you find one of them and then you can find the other. Does that help? Any other questions? Here's another one. This is conceptual. We'll see. Same reaction, same amount of reactant. So we're conducting this in a bomb calorimeter and in a coffee cup calorimeter. In one of the calorimeters, Q for the reaction is negative 12.5 kilojoules, and in the other, Q is negative 11.8 kilojoules. Which value was obtained in the bomb calorimeter? You know, as I'm reading about this, I really don't care, and so I'm pretty sure you don't care either. Yeah, let's not talk about that.